Can you hear me?
Hey, Pratik, are you there?
Yeah, I'm here.
All right, how's your day going for you?
Pretty good. I mean, well, yeah, good enough.
Okay. Anything going on in your class that you know about, or?
Uh, right. So we had a quiz.
Hmm.
I think we talked about it last week, 6.1, 6.2.
Hmm.
Did pretty okay on that.
Good,
Um,
good.
yeah, that's good. So, Friday we learned about logs, right? What we
Okay.
talked about the class before that. I mean, we started off, but we talked about it on Friday. And today we talked about graphing logs.
Okay.
Well, I haven't done the homework for that one yet because we literally did it today, and I
Okay.
just got home like half an hour ago. But yeah, I did the homework on logs 6.3. That went well. Didn't have any issues
Hey, I'm
at
glad to
all.
hear
Actually, that
that.
was really easy. Huh?
I'm glad to hear that.
Yeah, yeah. I am. Yeah. I mean, it kind of makes up for like the whole chem test I had today. That wasn't good at all.
Oh no, what happened there?
Well, uh, so basically, what our course does is we have marking period tests. So it's like a lot of studying prior to it. And
Hmm.
I thought I did well, but there's a couple of problems I didn't know. And then like a lot of the other kids were like also freaking out, like a lot more than I was freaking out. So that makes me think I should have been freaking out. So do you see what I mean? Like not sure how I did, and it's concerning.
I see. What topics are you talking about in chemistry?
So this test was on everything we covered this quarter, and that was gases, electrons in atom, the periodic table, like electronegativity, ionization energy, and like
Okay.
trends, right? And then we did reactions as well. We haven't gotten to redox yet, but
Okay.
um, we did like just like decomp, synth, single replacement, double replacement,
Okay. Okay.
combustion.
Did you like
Yeah.
covalence bonds and those things as well, or?
Bonding is unit 9, so we just started that.
Okay. Okay. Yeah, it's been about 20 years since I done anything in chemistry, but I kind of remember some of those topics for sure.
Yeah.
Titration was one of them.
I see.
Okay, now the class, you're doing stuff on logarithms, and you did pretty good on the last quiz, right? You said,
Yeah. Got
okay,
a 93, I think.
that's fantastic. So that's definitely gonna move your grade up now, isn't it?
Yes.
Okay, so we want to keep this momentum going. So you you got to learn how to graph, and you're learning how to solve logarithmic equations. Did they give you some problems you want to work on here for today?
Yes, I think so. Today we worked on graphing logs and also finding the inverses of logs. So if you have problems in those things, that'd be nice.
Okay, sure, sure. Let me see what I
Yeah.
have here. Did you have anything in particular, or
Nope, just practice. Practice is good.
okay? Let me grab some problems here. Give me a moment.
She was trying to be nicer, but at the same time, it's not nice. You know, it is. It is. Hold on.
Did you say
Yeah,
something there?
she.
Okay, I'm gonna throw these problems up here real fast. I want to see if you can maneuver through these. Have you looked at these yet?
Give me one sec. All right. Well, oh my God. So this is just isolating X, right? Then
Mm-hmm. Why don't you take
yeah.
30 there, and let me see how you're going to approach number 30.
Number 3, like so 32.
Number 30, see if you can solve for x for number 30.
Oh, okay, cool. Um, Trying to think. Is it Yeah, I have a question real quick before I like do this problem. When you
Mhm.
multiply, I don't know why I keep forgetting this, but I do. When you multiply, do you multiply the bases and add the exponents, or you just add the exponents and keep the same base?
Whenever the bases are the same, you're multiplying exponentials, you would then add the exponent. Now, if you're
So the
not for
base stays the same?
sure, yeah, let's look at a few examples here. So let's say if you're on an exam and you got all these rules and you just kind of forgot which one's which. Here's what you can do. Just jot off to the side, put out some powers of 2, like 2 and 2 squared and 2 to the third and 2 to the fourth. And if you have 2 to the first, that's 2, and this is going to be 4, and this is going to be 8, and this is going to be 16. And just kind of play around with it. Use the example to try to find that echo of truth. So if you take 4 times 8, that's going to be, of course, 32. But 2 is going to be 2 squared, and 8 is going to be 2 to the third power. And if you go one more, 2 to the fifth, that is 32.
Oh,
And
I
right
see.
there, you see a to the n times a to the m is going to be m plus m. Now, likewise, you can also do this for all the different properties out there. Let's say if you're going to take 8 and you're going to square it. If you take 8 and you square it, you get a value of 64. 64 is
Mm-hmm.
going to be one more down here, 2 to the 6. But 8 is also going to be 2 to the third power. So notice what's happening here. If you were
Yeah,
to power up an exponential, you take the product.
I see. Okay. That's helpful. Thank you.
Mhm. So if you get lost, just imagine just a real quick example with these powers of 2, so you make sure you get it for certain.
I
So for
see.
that very first problem there, you see where it says 3 raised to the power of 2 to the x?
Yeah. So I
Here's
would
what we
keep
do.
3 and then 3x.
You're going to take the 3 to the 2x, and you're going to apply that property we just looked at. Now, if you can make it, you can break it. A lot of times we talk about simplifying, but what about unsimplifying? So I can go backwards and forwards with the properties however I need to.
Mm-hmm.
So you can take this and you could rewrite it like this, because x times 2 is 2x. Now, the benefit of doing this is if I take this equation and if I was to re-express it, recalibrate it,
Right.
see what you can see here now. What do you have? If it's hard to see, sub it out. Suppose u equals 3 to the power of x. U squared minus 6u plus 9 equals 0. It's a quadratic in disguise.
Oh, wow.
And if I want to do a quadratic and solve for it, I can factor it. Or if I can identify some kind of structure, I can get to the answer a whole lot faster. And I see that u is going to be a value of 3, but I remember that u is really going to be 3 to the power of x. So I take that, I drop it in, and I realize x is nothing more than 1. And when I come back to the original problem, it makes a lot of sense. Because if I say 2 times 1 gets me 9, minus 6 times 3, and then plus 9 again.
Yeah.
And there it is. So we have 18 minus 18, which in fact is going to be 0.
What I was gonna do is I was gonna be like, oh,
What were you going to try to
log
do?
log 3 of, or no, hold on. Um, I was trying to do like log 3 of -3 equals 3x.
Yeah. There's a problem with taking the log, though, because the properties of logarithms, when you have an argument that has a plus inside, you can't really take it apart. It's all locked in place. But if you had a product inside your logarithm, property we were talking about the last time, you can take it and then you can recalibrate it like this. But
I
think like
see.
the plus signs and minus signs is like a gear in the system, and the clock works. It just grinds to a halt, and you can't do anything with it.
Oh, okay.
So let me pull down here. Why don't you try 31? See if you can solve that one now.
And then, so that's the same base. So 4x to the third, right? Minus,
Okay, so tell me why you have it to the third power.
because you have it to the second here, and then you have it to the first here, so 2 plus 1 equals 3.
Well, you can't do that because there's a minus sign. All you really can do, you can't say 4 times x. Because
Oh, I
that's,
meant 4 to the x. Sorry, I meant 4 to the x. I did not mean 4x times x. I meant 4 to
okay.
the x. So
Well,
would it be 4 to
that
the
you can
3x?
definitely do. That'd be to the second power still.
Why not the third?
Because I can't say this is going to be 4 to the third power.
But I'm like trying to combine these two.
Well, you can't because there's that minus sign in the middle. See, the properties of exponents only permit you to add up the exponents whenever you're multiplying. So if I have a to the n, a to the m immediately being multiplied, then I can add up the exponents. If I try to add up the exponents, let's say if I have 5 squared and I have a 5 squared.
Mm-hmm.
Well, what's 5 squared? It's 25.
25. Yeah.
What's 25 plus
So
25?
50.
Is that the same thing as
50.
saying 5 to the fourth?
No.
No, not even close. So properties of exponents, I have to make sure that there is a multiplication and not a plus sign or a minus sign. Otherwise, game over. They're not going to work. But what you could do is you could recalibrate using this property, the power property. And that's going to give us a different viewpoint of how to approach this problem now. We'll have a minus 36 or 63. We'll have our x up top still on top of the 4 and minus our 64. Change your perspective. Look at it differently. Set equal to u. And see what you see. Okay, give that a try.
Hmm. Hold on. Yeah, okay, that works.
You have 2 answers now, don't you?
Yeah, so now you say
4 to the power of x. Let's take that x that's put on top.
oh yeah, sorry, yeah. And then
All right, Pratik, riddle me this. For what value for x do I need so that power up of 4 and I get something that's negative?
I feel like that would be undefined.
It's not going to work, is it?
No. Yeah.
Look at your graph for your exponential. What does it look like? Takes off.
Yeah.
I'm just kind of curious. This is going to be the graph when I have exponentials whenever my b is going to be bigger than 1. Always going to look like this.
Mm-hmm.
And where's it going to cross right here?
The y-axis,
And what's that value?
x equals 0.
You got it. So 0, 1, that's going to be a nice fixed point for any
Mm-hmm.
exponential. That's valid, as long as it's
Mm-hmm.
bigger than 1.
Yeah.
Am I ever below the x-axis?
No.
No. So this right here is an erroneous solution. You throw it out. What about this
But
one?
you know that 4 to the third will give you 64. So therefore x equals 3.
Okay. Let's be a little bit more systematic about it. We'll just throw it out here. We have 4 to, oh, yeah, right there, 4 to the third, and we have our x value.
Mm-hmm.
And we'll just make a match. Now, the reason why I'm doing this is what if I had the problem where it got set up for some reason let's say if it was 2 to the x plus 1, and you found out that it actually equals 64. See, it's a little bit more challenging now to make it all equate. We can do it. Let me take the 64 and first express as a power of 4. Then, as soon as I have that, unlock the exponents, make them equal, and solve for x. And there it is.
Why would we set them equal though? Because the bases are not the. Oh no, they are. I see.
That's
Okay.
right. You
Oh,
just
okay.
answer your own
Okay.
question, didn't you? Make the bases
Yeah.
the same. And if you can do that, man, they're easy. It's when they're not the same, that's where you have to kind of pause a little bit and do some stuff with logarithms.
So in this case, if you want to use logarithms, you would have said log 4 of 64 equals 2x plus 1, right?
You most certainly could.
And then you would, actually, could we say like log 4 to the third?
You sure could. And you can
Okay.
pull the 3 out front.
So like here.
Like this. That's one of the properties for logarithms. But if you have a logarithm whose argument matches the base,
Isn't that just 1?
that collapses down to 1. So you could take the log, or you can just note since the bases are the same, it's a little faster just to equate them.
Yeah, I mean, that makes sense. I was just trying to see like the workings behind it, so that's why I did the log thing first.
Now, if you
That's
had
cool.
different bases, this is when you want to use a log. And it doesn't matter which log you use. You can use a common log, natural log, base 4, base 3. It doesn't matter. Just take a log and throw it at it.
Let's see.
Use your properties. You can say this if you like. And then solve for x. Bring 1 over to their side. And then divide by 2.
I see.
Good. Well, let me pause. See if you have a question about any of that.
No, but I'm just trying to see to make sure I recap. So, is it okay if I annotate for your work?
You go right ahead.
Okay. So you're bringing this out through property of exponents to here, and that's where you got this, right? And then you're left with log 4, because you chose any log and you chose e, right? And then after that you 3 log 5. How did you do that? I don't understand that part. That's the one thing I don't. Because
Property
wouldn't.
of logarithm stipulates if you have a logarithm, doesn't matter which log it is,
Mm-hmm.
and if you're powering up the argument, you can pull the power out front. Just like that.
This I got, but how 3 log 5. See, okay,
Which
so it
part's
would have been
confusing you?
2. Okay, well, one sec. Give me 1 sec.
Go ahead.
Log 4. Okay, so if you take 4 2x plus 1, do you see my work? And you want to say, so you said, so you would have said like log e of 4.
Well, what's log e of 4? That's not exactly what you have up there.
Hold on. Oh my god. Oh, just log
Let's
of.
move this down a little bit for us. There you go. So if you take the natural log, you can. Don't write e out because it's already understood. Or if you want to write the e out, then say log base e,
Yeah.
which is going to be this. So if you take the logarithm, let's say the natural log of this particular value,
Mm-hmm.
take your exponent, yank it out front.
And this works for any log. It doesn't just have to be natural log.
It works for any log. Base
Okay.
10, base e, base a half, 2, it doesn't matter. Because you're really using the properties of logarithms to, pick an apple from the tree, I guess. Just trying to take it and bring it down. You're throwing a log at it. And this is one of the reasons why we want to look at logarithms. A logarithm really is a type of exponent. That's what this property is really echoing. And you can always go back to any logarithm you want by using that change of basis identity for the
I
log.
see.
Now, in class, they're going to say, hey, you got to take log base 4. No, you don't. Any log would work. Or log base 3, they might tell you. No, you don't. You can just always default to the natural log if you wanted to. And you could convert at the very end using the change of basis identity if they want you to do that. The change of base identity, again, is whenever I have a log of any base of my choosing, I can convert this to any base of my choosing. Log base A, for instance. Now, oftentimes this is kind of challenging for students to really comprehend that you can choose whoever you want. So we just make it a little bit easier. We make the choice for you guys. We just say, okay, just call it natural log. Or we might say just call it common log.
Mm-hmm.
But it's really anything you want.
I see.
Okay, good. Well, let's look at that last problem up here. Let's see if I can get that back on the screen. Uh-oh. I'm all over the place trying to grab it. Okay, here we go. 32.
There we go. Okay.
Okay, I'm gonna give you some more room here. Give it a try.
So hmm?
Okay, now always want to go back and double check to see if they actually are valid if it doesn't work out. Okay, so
Okay, so
if u equals
1.
3 to the x, if you plugged in 0, does it work?
So you have 0, so that's 1 minus 10, which is -9 plus 9. Yes, it does work.
Okay,
And 2 is 4, so 81 minus 90 equals oh god, -9 plus 9 equals 0. Unless I did that math wrong, because that was really quick.
okay, so 2 to the 4th is 81.
2 to the 4th?
Or excuse me, 3 to the 4th.
Yeah.
Okay, and then you're going to subtract off.
Subtract off 90.
Okay,
That's -9, right?
and then add 9 to it.
So it is 0. Yeah, that works.
Good. Okay, any questions about these?
So this particular problem has 2 solutions, right? X equals 0 and 2.
It most certainly does. So you
Okay.
have sometimes 2 solutions, 1 solution. You may even have no solutions. That's possible.
Let's see. Okay. I
Okay,
think I
so this
got
gives
that.
you a nice jump start, head start when you start getting into that here pretty soon.
Mm-hmm.
Let me throw this one to you. You said you're talking
Okay.
about graphing today.
Yeah.
Could you actually graph A, B, C, and D here.
The graph of y equals log x is shown. Sketch the graph of sketch the graph of log equals 10 x plus 2. So would you just move it over to, or move it back to, or like to the left 2 units?
Okay, why would you move it to the left?
Because I've never really understood this, but like anytime it's like with an x, whatever sign it is, you do the opposite of that.
Okay.
Is it because it's x minus h?
Yeah, it is. Now, let's take a step back and we'll look at a parabola real fast. If you were to graph a parabola, just the base graph x squared, it would look a little bit like this.
Yeah.
Now, let's say if I do a function composition and I create a new function called g. If I plug in x plus 1 into this function, I get this one right here. If I was to graph this function, let me ask you this question. When will it cross the x-axis, or when will it touch it?
When will x plus 1 touch the x-axis?
Mm-hmm.
At 0.
Not 0. When x equals
Oh, I mean not 0. I meant -1. Yeah.
-1.
I was thinking of y, sorry.
And if I was to do the function composition and create
Mm-hmm.
function h now, and say x minus, you can follow that vertex. Where's that vertex going?
Back to x equals 0.
It goes over here to 1 now. See, whenever you do function compositions, you say x plus c, follow that vertex. Suppose this thing equals 0. And you see that in order for that to be 0, what you have to do is trace it back and say c units to the left. So whenever you have that plus right there, it's going to be to the left. When I have the minus, it's to the right. Probably the best way is follow the vertex. Follow a key feature of the graph and trace it out.
I see.
So if I go back to the logarithm, I can do something really similar. I can follow what's going to happen here at that dot, but I also note since it is a logarithm, I do have a vertical asymptote over here at 0. Now, in order to cross right there on the x-axis, my output again needs to be 0. And the only time that's going to occur is when x equals 1. Follow the vertex. What they need for x plus 2 to be 1, in other words,
I see.
-1. So it's got to go 2 units, 0, and then one more, -1. Sketch out your graph. Okay, so compositions, horizontal shifts, and if I add to the graph, like add 1, add 2, that's a
Mhm.
vertical shift, up or down.
Gotcha.
Okay, try B now.
Is that it?
Shift over to the right by 2 units. And if you were to plug in 3 into your graph, what happens? You get 0 for y, don't you?
Mm-hmm.
Okay, now C, that's an interesting one. See if you can put this together.
Negative x. Let me see. Is that it?
You got it. Why'd you do that?
Because I know that if you have like an equation and if a is negative, then you reflect it over the y-axis. But if the x term is negative, then you reflect it over the x. Wait, I said that the other way around. If a is negative, reflected over the x-axis, with y. If the x term is negative, reflected over the y-axis.
Right, so you reflect it if you're multiplying by a negative on the outside of the log and inside, not the y. Good.
Yeah.
Are you ready to take it to the next level?
Yes.
Let's bring it. Here's number 3.
The diagram shows part of the graph y equals log 5 of x. Find a and b. Okay.
Okay.
How do I do that?
So when is my logarithm equal to 0?
When my logarithm equals to 0
Mhm.
is when never.
Well, it does equal 0. It does cross the x-axis. So
Oh,
in order
well,
to
that's true. So
cross,
it has to equal
yeah,
0 at some point. So x, so if you rewrite this, you would have to rewrite it as 5. X is 1. X is 1.
that's right.
Okay. I don't know why I see that early. Okay, cool. So
Now,
A would be 1.
there's a
B would.
property too you can use. Remember that property? Exponentiation.
I don't think so.
Okay, your exponentiation property, this is going to be exceedingly useful whenever you start solving your equations. Sometimes it's referred to as powering up. But if you say 5 to the 0, that's 1. And here's a property over here for logarithms. If you exponentiate a log with the same base, whatever's right here pops out. Okay, so that's how you can do this algebraically if you need to. Okay, so we got a is 1.
So let me get
What?
this straight. So it's 3 equals log 5 of x,
That's
right?
right.
So if I say 5 to the third, and then if 5, so does 5 equal x?
No,
Is that
because
just
you have
saying?
5 to the third on the left. That's 125.
Oh, yeah. Oh, I'm actually kind of broken. Yeah, 125.
Okay, so we got A and we got B.
Sketch
Now,
the graph of y equal log 5x.
okay, let me give you a little more room there. Let me just erase some of this. All right, there you go.
Um, excuse me 1 second. Okay. Sketch the graph of y equals log 5 of x. How would I? So 5. So does that? Okay. Well, so when when a is greater than 1, it's a vertical stretch unless it's between 0 and 1, right? Then it's a horizontal stretch. So how would I do this?
Well,
Sure. Oh.
see where it crosses the x-axis to begin with. What argument do you need for x where it is to?
1.
So your argument, it needs to be 1, but you have 5x.
So if it crosses the x-axis when x is to the power of 1, but then it's 5 of x.
Yeah.
So
Take your argument.
You need to pick
5x. make it 1. X needs to be a fifth. Because if X equals a fifth, you plug it in, you have log base 5 of, not 5,
1.
not 0, but 1, which is an output of 0.
So base, okay.
Okay, so you got that data point. And really, particularly, it's going to have the same shape. I wouldn't stress too much about it, at least for right now.
Mm-hmm.
Just imagine you're doing a little three-pointer and basketball.
Okay.
Okay, that's basically what all these graphs are going to look like for you. Now,
All right.
they might be a little more, shifted down, like a little flattened out, or a little bit longer. Don't stress about that for right now. Later on, we can talk more about more accurate graphs. We can learn a little bit more about the structures of the functions, like we do in
Okay.
calculus. But for right now, this is good enough.
Okay.
Okay, try C though. That's a little more interesting problem.
Sketch the graph of y equals. Is it okay if I erase some of this?
Go ahead.
Okay. Sketch the graph of y equals log. Oh, okay. So what you did earlier was you said x. I don't understand this. This is
Okay,
difficult.
now that's good. You're a little confused, right?
Mm-hmm.
Now, ask yourself, why are you confused?
I don't get it yet.
Okay, so let's go a little further. What's different with this problem that you can't do that you can do with the other problem?
That one is being
Square, isn't
multiplied
it?
by 5. This one is being raised to a power.
Good. Bingo. If it's being raised to a power, focus your attention on that then. Problem solve it. See, you're saying, I can't do this because there's a 2 there. Okay, get rid of the 2 then. What does it look like?
Do you bring the 2 out front? 2 log 5.
You most certainly do.
Oh, okay. Okay.
Okay, so you can do that. And we're going to say x is going to be these non-negative values again.
Mm-hmm.
And you're still going to get that vertical asymptote over here on the right-hand side.
Yep.
But that 2 is going to, you still got that fixed point, but it's going to scale it. It's going to look a little bit more like this. Okay,
I see.
so whenever you're looking at your problems and you're like, man, I don't know how to do it, always do a follow-up. Why can't I do this? Well, it's because of that 2. If that 2 wasn't there, I'd be able to get my answer real fast. And that's given the dead giveaway that you should focus your attention on that problematic piece and try to convert it to something that's more manageable. Look at D. What's really strange and hard about that problem?
X is um the denominator for a fraction.
Okay. Now, wouldn't it be a whole lot easier if I went back to this instead? So it's
Yeah.
hard because I have a fraction. So
So we
what am
multiply
I
both
going to
sides
do
by
about it
x.
to get rid of it?
Multiply both sides by x.
Can't do that because it's inside of a log. But I do have a property of logarithms I could use. If I take a logarithm and look at the ratio, remember this property? I could take this and recalibrate it, just like this. Look at my difference. So here I have log base 5. I can express it as log base 5, 1 minus log base 5 x. And what's the log base 5 of 1?
0.
So what is this really saying?
Negative log base 5 of x.
Yeah, that's what we have to graph. Now, go back and see if that's making sense what I'm trying to tell you. Identify the problem, focus your attention on the problem, and formulate a solution using the different properties you have to overcome that problem.
This makes sense.
Good, good.
So I'm just trying to figure out. I kind of didn't get how you did that. So why did you say x is equal to 1/5 here?
In order for it to cross the x-axis, y needs to be 0, right?
Right.
Okay, so if I
Oh,
just set
right,
the
that
other
makes sense.
side,
And then 5x needs to be 1. So how do you get 5x to be 1? You multiply it by 1/5.
that's exactly right. Or
Okay,
you can just
okay.
go ahead and exponentiate, and you see the same thing.
Yes. Okay.
All right, let me throw another one of these.
I need to work on exponentiation, I think. Using it at least.
Okay, see if you can go through all these now.
I don't know. Okay. Diagram shows part of the graph y equals log 4x. Find A. A. So y is 2. So what does x have to be in order for 4 to the 2 equals x? 16? So they have to be 16.
Doing good.
B. Sketch the graph of y equals log 4 to the x. So oh, we talked about this. So you said it needs to cross the y-axis. So the x-axis. So we need to make x be a fourth. So is that it?
Keep going.
Okay, and then for C, sketch the graph of y equals okay. Y equals log 4x to the cube. So you said cube is the issue, so you do 3 log 4 to the x. And that would just scale it up and look something like this. Well, that's a horrible drawing, but like
Yeah. So you identify that problem, that cube there.
uh,
Man, I wish that 3 wasn't there. Well, what are we going to do about it? Properties of logarithms.
yeah,
Pull it out front.
got you. And if it was dividing, like, what was it like? It was like 3 divided by x log 4.
Yeah. Let me give you a little more room there. There you go.
What would you have done? I forget. Don't tell me 1 second. I can't remember. Would you have? Oh, -3 log 4. Log base 4. Log of base 4. Would that have been it?
Not quite. See if you can remember that property again. That's not quite right.
There's definitely a negative in the front. I remember that.
Well, there was a reason why it was a negative.
Negative log 4 of 3.
Okay, well, I'll
Kind of
put it
guessing
out
it.
here, see if you can beat me to it.
Oh, you're adding the, hold on. No, you're not adding, subtracting. So log of 3 minus log of x.
That's right.
So,
Vertical shift, reflection. So you would have the log and then reflect it, then shift it up. Translations.
I see.
Okay. Yeah, it's actually a pretty good problem there. It's a little more challenging.
Mhm.
All right, let's take it to the next level. Ready? Try that one.
The diagram shows the graph of y equals log b x plus a. Find the values of a and b. Okay.
Okay, let me give you a moment there to think about it.
Wouldn't I just plug in the values first?
You might, but go, I'll let you think about it here for a second.
X plus a. Does x plus a need to be equal to 1? So that the x-axis still crosses, or the graph still crosses the x-axis, or something like that. Log b. Log b. Okay. Hold on. I just want to write this in exponential form to see if I can.
Okay, so you feel like you have a good answer how to approach it, let me know.
No. No, that's exactly what it is, actually. No, hold on. Is that it for A? I'm not sure.
Okay, so tell me what you did here. What was your idea?
So this was actually shot in the dark, but I said, so I did this, right? Where you,
Mm-hmm.
so you said if you put the same base to both, then you can have, well, I feel like I just converted to exponential form, not the line.
Okay, well, yeah, that's not bad approach. Let's just go through your idea. So you exponentiate it because you said, well, I don't want to work with a logarithm. Maybe an exponent can be a little easier, which is fair point. Maybe that's what you want to do. And you recovered the argument. Brilliant. Okay, and then you
And
say,
the,
okay, y needs to be 0.
Yeah.
B to the 0 is 1.
Yeah.
And so, okay, what does that then make A then?
So I said now I can sub in x because I know what x is.
Ah,
So I said 0, sorry, 4 plus a. And then I said 1 minus 4 equals -3, so -3 equals a.
okay, so we have a pretty good idea that looks like we have log base. And we got our B, not really telling us what it is here at the moment, but we know that, or at least we think we know that whenever you plug in a -3 for A. Well, I have 4, plug it in, I guess me 1. It works out, doesn't it? Okay,
Mm-hmm.
great job. That's exactly it.
Cool.
Okay, now see if you can figure out what the B is going to be. Use that data point to figure it out.
Is B2?
Well, let's see. You have 4, you have log, you have B, you have 16. Oops, kind of in your way there. And what you do next? You exponentiated. Good. 4 through. You got it. That's awesome.
Okay.
Good, good. Let me throw you one more. So you can find A and B now. Notice a slight subtlety.
Hmm. Wait. That would not work.
Okay, I'm gonna give you a little hand. Plug in 0 for the Y. And for the X, we'll plug in 4. Now, you definitely put that back on top, and you're going to exponentiate like you did. Okay, see, you do have this system you can work with, but you also might want to consider this system up here using the point. And if you do something pretty similar, what you're going to come up with is 3 to the 6 equals 4 minus b to the 30th. Oops, sorry. 30 inside. We'll have our B, and then we'll have our A.
Three to the sixth.
Uh,
Oh, okay. Got you.
Yes.
Yeah,
Why
I
it's
see
gonna be
it.
6?
Why does this change anything?
You have two variables, and if you want to solve a system, you have to have two equations.
Oh, you're right.
So you have to find a way to blend these together now. Now, there is a problem with A being an exponent, so you might want to take it back and look at a logarithm. So if I did take it back to a logarithm, that would correspond to 0. Take the log both sides. And really, I can take any log I want. I'm going to take the natural log. You can go log base 3 if you want to. It doesn't really matter. But I'm just going to lay this out here so you can at least see it. And I'll let you play around with this later on. And I want you to give this some thought about what you might be able to do to get going. I'm going to give you a little hint. Big hint. What if you divide? This goes in the 0, 0 times. A over A is 1. You're left with log 4 minus B. What's the only time that's going to be 0?
What? Say it again?
What's the only time that's going to be 0?
When B equals when the log equals like log of 1.
So B's got to be 3. And if you come back up here, it makes a lot more sense, doesn't it? 4 minus something powers up, you get 1. 4 minus B better be 1. So B's going to be 3. What about A?
Hold on. So 4 minus B equals 1. So log of 1 divided by log of 27. That just gives you 1 over 27, though.
Plug this
Sorry,
into
log of.
plug it now into the yellow. 3 to the 6, 27. Remember what we said a moment ago about making the bases match?
3 to the third.
Good. Properties of exponents come to the rescue. What's A?
So oh no, God, no.
A's 2, isn't it? You're
Yeah.
getting there. Well, good. Well, Pratik, how do you feel about things? You feeling all right with it?
This one was a bit iffy, but the other one was pretty good.
Yeah, it's a little more challenging than this last one, isn't it? Good. All right, well, keep practicing these topics with graphing. Just remember horizontal, vertical shifts. And it seems like since it's an honors class again, they're going to be asking you to find things like A's and B's. So you got a good head start on that.
Thank you.
All
That's
right. Well, if
good.
you need anything, let me know. Otherwise, I'll see you next week, sir.
All right, you too. Have a good week. Bye.
All right. Take care. Bye.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.